start. So our last speaker for this afternoon session is Sahiba Arora. I hope I pronounced it correctly. from Dresden. And she also wants to talk about eventual positive semigroups, but now on another topic, namely the spectrum of eventual positive semigroups. And please, Sahiba, the stage is yours.
Thank you so much for the introduction, Christian. And thank you all for coming to my talk. And thanks, Jochen, for inviting me to give a talk. Always glad to talk about eventual positivity. Though now that I have to talk after you, so there's a lot of pressure. But let's hope I do justice. So this is, of course, joint work with Jochen Gluck. So let's start. We have an abstract Cauchy problem where A is a generator of a C0 semigroup, right now only on a Banach space E. Then the Lyapunov theorem says that in finite dimensions, the spectral bound of the generator is equal to growth bound of the semigroup. Here, the spectral bound is just the supremum of real part of all spectral values. So this is well known that in finite dimensions, spectral bound is equal to the growth bound. However, if you look at infinite dimensions, so say now we have the space L2 intersection L4 on the half axis, and you take just the sum of the two norms on the two spaces, and you take the shift semigroup, then one can easily compute that the spectral bound is -half, but the growth bound is strictly larger, so it is -1/4. And this example shows that Lyapunov's theorem fails in infinite dimensions. But this is, of course, not new. This is very well known to people who are familiar with semigroup theory, that the spectral bound need not be equal to the growth bound. So once we find a counterexample to something, now our next question is, can we find some weaker conditions under which the result remains true? And one such class of examples one is interested in is in positive C0 semigroups, because in applications, there are a lot of examples of semigroups which are actually positive. So, and positive C0 semigroups have very nice spectral properties. So it is a natural question to ask whether Lyapunov's theorem holds in infinite dimensions for positive C0 semigroups. So since we're going to talk about positivity, we need some order on the space. So now we have an order Banach space, or you can just think of any function space. Let me just recall that a C0 semigroup is positive if each ETA is positive. So that means it maps positive functions to positive functions for all time t greater than equal to 0. And now one asks whether for positive C0 semigroups, does it always happen that the spectral bound is equal to the growth bound? But one does not need to look too much further, because this semigroup, which we've already seen, is positive. So Lyapunov's theorem fails for positive C0 semigroups as well. So then now, okay, so it is not true in general. It is not true in a condition in which we expected. Then the next question is, are there some special cases under which the result holds? And that is this well-known result, not one result, but a lot of results combined into one. So let's look at some sufficient conditions under which Lyapunov's theorem is true. And this is already, since Lyapunov's theorem for C0 semigroups has been studied a lot, so this is all the conditions here are well known. So we start with the C0 semigroup on a Banach space E, and we let omega be just some sigma finite measure space. Then we have that the spectral bound is equal to the growth bound if the semigroup is analytic, if the space is L infinity. So now it does not matter what the semigroup is, what the structure of the semigroup is. Once you have that the space is L infinity, then for each C0 semigroup, it is true. Third, if the semigroup is positive, and of course it does not end here because we've already seen that for positive C0 semigroup, it is not true in general. So we need some further conditions in addition to positivity of the C0 semigroup. And those are if E is an L2 space, or in general an Hilbert lattice. Second, if E is the L1 space, or in general an AL space. And this was shown by Derdinger in 1980. Third, if C is the space of continuous functions vanishing at infinity on a locally compact space omega, and this was shown by Charles Batty and Davis in 1983. So in particular, this holds for the spaces of continuous functions on a compact set, and more generally, it's also true for AN spaces. Lastly, it is true. So L infinity, L2 and L1 cases are already covered. For L infinity, we do not need positivity of the semigroup. Finally, it was answered that for LP also the answer is yes. So it's true for all LP spaces for P in between 1 and infinity. And this was first shown by Weiss in 95, and he gave a shorter proof in 96. However, the shorter proof is also quite complicated. And last year, Henrik Vogt gave a much simpler proof, much shorter and much simpler proof for LP spaces. Okay, so this is a well-known result. So this is nothing new. And even Vogt's proof is just, right now is just another proof of a well-known result. But so Vogt gave an example for, gave a proof for positive C0 semigroup on LP spaces. And the proof is much easier. So the only complicated proof that remains in this result is for C0 spaces. So the proof for positive C0 semigroup on C0 spaces uses arguments like it really depends on the dual structure of the space, so the spaces of measure, and it uses the sun dual of the semigroup to show that the spectral bound is equal to the growth bound. Now the problem is that the dual generator, so the dual of A, need not generate a strongly continuous semigroup. It is only in general a weak star generator of a C0 semigroup, and that is why the proof gets really complicated, and it does not really highlight the structure of the space C0. So we can adapt actually Vogt's proof to give an alternate proof for the C0 spaces. So let's look. So the theorem is this, that on positive C0 semigroups on C0 spaces, the spectral bound is equal to the growth bound. So now I'm claiming that the proof is simple. So I have to show you the proof, especially because it is a classical result and I cannot just claim that the proof is simple. So let me give you a proof and try to convince you that the proof is really easy. So in order to show that the spectral bound and the growth bound coincide, I claim that it is sufficient to show that if the spectral bound is negative, then the semigroup is bounded. Why is this true? Because if the claim holds, then for each alpha between the spectral bound and 0, we have that if the spectral bound is smaller than alpha, then the rescale semigroup generated by A minus alpha is bounded. And that would imply that the growth bound is less than or equal to alpha. And because alpha was arbitrary real number in the interval SAN 0, so we get that the growth bound has to be less than or equal to the spectral bound. And the other inequality is actually always true, that the spectral bound is always less than or equal to the growth bound. And so this is actually, so it is actually sufficient to show that the spectral bound is negative, implies that the C0 semigroup is bounded. So now that we have this here, we are going to prove the claim. So to prove the claim, we start with the assumption that the spectral bound is negative. And we start with a positive function f in C0. Now we have a continuous function on a compact space Z0 So this set is bounded. The set of orbits on 0, 1 is bounded, is compact, sorry. And because it is compact, it has a supremum. And let's call the supremum G. And in fact, not only is G just a supremum, G is also positive, which I forgot to mention here, because each F is positive and the C0 semigroups are, C0 semigroup is positive. So each of these functions in the set are positive, and G is a supremum of positive elements. So G is also positive. Now, the main argument. So we fix a time t greater than or equal to 1, and we fix a unit interval I equal to t minus 1t. Then, because I is a unit interval, one can just simply write that ETAF is equal to the integral over I of ETAF ts. Now we apply the semigroup law because S is in the interval I, so T minus S is positive, and so the semigroup law here, we can use the semigroup law. And now what we have is that this is bounded above by the function G, because G is the supremum of all ETAF such that T is in 0, 1. And here, because S is in I, so T minus S is in 0, 1. And so ET minus SAF is bounded above by G. But also because the C0 semigroup is positive, so the operator ESA is also positive. And so ESA applied to this is less than or equal to ESAG. And of course, it holds with the integrals as well. And finally, now we use a property, another property of positive C0 semigroups, which is that, so in general, if you have a C0 semigroup, then it is well known that the Laplace transform representation of the resolvent is true everywhere on the right of the growth bound. Positive C0 semigroups have this very nice property that this representation also holds everywhere on the right of the spectral bound. And since the spectral bound was negative, so in particular for positives for the semigroup, it holds at 0. And so this is actually equal to, less than or equal to the resolvent of A at 0 applied to G, which means that we have shown that the orbits are bounded for all positive F and E. But since we have C0 space, so the positive cone is generating, which means that one can write every function as a difference of two positive functions. So we have actually shown that it is true for all F and E. And so by the uniform boundedness principle, the semigroup is bounded, which completes the proof of the result, because that's all we wanted to show by our claim. Let's see how I'm doing on time. Okay. So, so this was the result for positive semigroups, which was known before, and now we just have an alternate proof. Now, Jochen spoke about eventual positivity in his previous talk, and so the question is whether such sufficient conditions for Lyapunov's theorem also hold for eventually positive C0 semigroups instead of just positive C0 semigroups. And the result, one naturally expects all these results to carry to eventual positivity, is because, as I mentioned while showing you the proof, that the Laplace transform representation of the resolvent is true on the right of the spectral bound for positive C0 semigroups. The same is true for individually positive C0 semigroups, that the Laplace transform representation of the resolvent is true. And so using that, one shows that eventually positive C0 semigroups have very nice spectral properties. And so it is natural to ask whether eventual positivity also, this theorem also holds if we replace positive C0 semigroups by just eventually positive C0 semigroups. So first of all, let me just quickly recall that the semigroup is called eventually positive if there exists a time t0 such that each operator ETA is positive for all times t greater than or equal to t0. Now, Jochen mentioned both individual and uniform eventual positivity, but I'm only sticking to the uniform eventual positivity for simplicity. But most of what I say is true for individual eventual positivity as well. Uh, and so once we have the definition of eventual positivity, we can insert eventually word here. And so the result remains true without any changes, except we have to now change the citations. So the case for L1 and L2 was shown by Daniel Danners, Jochen Gluck, and Kennedy in 2016. The case for LP, for general P, was actually Vogt's proof. So I mentioned that he gave a proof for positivity, but actually he gave a proof for eventual positivity, and it works for he gave a proof for eventual positivity, and that's generally, of course, in particular true for positivity as well. And now the previous proof that I showed you can be adapted using some bare category arguments to show that it can actually be adapted to this case of eventual positivity as well, which is the second advantage the previous proof has. So it's not only easy, it can be adapted to the case of eventual positivity, which was not true for the previous known results, because the previous known results really concentrated on the behavior of semigroup near time t equal to 0. And once you have eventual positivity, you don't know anything about what happens at time t close to 0. And so you cannot adapt all those arguments because they show something like that the domain is a sublattice, and that you cannot really adapt those arguments to show that the domain of the generator is a sublattice in the eventual positivity case. But the previous argument can, of course, be adapted to the eventual positivity case because it does not have anything to do with time closer to 0. Okay, so this was Lyapunov's theorem. And now, since we've seen that eventual positivity also has nice spectral properties like positive semigroups, so I'm going to use this as my motivation to show you one more result about spectral properties of eventually positive C0 semigroups. So we start with a sigma finite measure space, omega, and E is L2. Again, I'm just sticking, this result is not optimal. It's true on general Banach lattices, but just for the sake, just to explain to you how the situation is, I'm sticking to the particular case of L2 here. So let's look at a pair of Frobenius type result by Greiner from 1982. So we have a positive and bounded semigroup on E. Then it is known that the boundary spectrum is cyclic. And by cyclic, we mean that if I beta is in the boundary spectrum of A, then so is each integer multiple of I and beta. So this is a very well-known result for positive bounded semigroups, and it has a lot of nice consequences. For instance, it has the following consequence, that if you have a positive and bounded semigroup on E, and the semigroup is in addition eventually norm-continuous, then the semigroup operators converge strongly as t tends to infinity. Now, how do you prove this using Greiner's result is because you have eventual norm continuity. So the boundary spectrum is actually bounded. And once you have a bounded boundary spectrum and you have Greiner's result which says that it is cyclic, so it can at most contain the point 0. Because if it contains a non-zero value, then it has to contain the integer multiple of all those values. And so then it has to contain, then it becomes infinite, which is not possible. So in particular, the point spectrum is, the point boundary spectrum is also contained in singleton 0. And now one can use Tauberian theorems, for example, the ABLB theorem, to conclude that the semigroup converges strongly. So this is known for positive C0 semigroups. Now, the question is whether this result is also true for eventually positive C0 semigroups. And for eventual positivity, the problem is that if you want to prove the corollary for eventual positivity, then the natural question you ask is whether one can show Greiner's result for eventual positivity. And the answer is, I don't know. we don't know. So this gives you another second open problem to eventual positivity. It's whether the peripheral or the boundary spectrum of an eventually positive C0 semigroup is cyclic. So we don't know that yet. But what we do know is that if you have an eventually positive C0 semigroup, which is in addition bounded, then the peripheral point spectrum is cyclic. So you cannot talk about the boundary spectrum being cyclic, but the point boundary spectrum is cyclic. And again, it means the same thing, that if I beta is an eigenvalue on the imaginary axis, then so is each integer multiple of I beta. And now once you have this, because you can see here that the proof only used the fact that the point spectrum is contained in 0. So eventual norm continuity again implies that the point spectrum is contained in 0 because the point boundary spectrum is bounded, and in particular the point spectrum is bounded. And then again, one can use ABLB theorems because for that one did not need any positivity arguments of the positivity properties of the C0 semigroup. So by this argument, the result is true. One can just write the result for eventual positivity as well, and nothing else changes. The proof remains the same, except of course with different citation. So that is all I wanted to talk about. I finished quite early, I think.